Okay, let's get started. So today we're going to start in on root finding and optimization. The next homework will be on this and will be available next Tuesday. The new homework, although enumerated incorrectly, is available and due Monday. Let me know if you have any questions or comments. Are there any questions I can answer right now, or comments, concerns? Okay. So I do want to mention one thing getting started. I'm going to now, from now on, actually have lecture templates for you. Basically, the course notes, except that I cut out pieces of the code that we will actually spend a little bit of time in class coding up. So this is completely, if you want to do this, it's just a little bit easier. If you look at the lecture notes and the code's already there, it's a different learning experience than if you have to come up with it yourself. It's only usually just a few lines of code, and it's the kind of the core ideas from the algorithms we're going to implement as well. So they look almost like the course notes, and of course, you still have the course notes to look at as well. So those will always be available on Courseworks, and I'll be updating those as we go so that they have the newest information on those. Okay, so this particular topic is important. Root finding, in other words, finding zeros of a function when is across a zero, and actually finding any value, because you can always move a function up and down and just turn it into a problem of finding zero. We like zero because there's all sorts of properties of a function that crosses the x-axis that we can use to our benefit. So that's exactly what we're going to do. Optimization is very, very similar. There are different techniques often applied. The thing about optimization is that one of the ways to find maximums or minima, depending on the question you're trying to ask, is, of course, to take a function you're trying to find optimum values for, take its derivative, and now find its zeros. So that's why they actually do kind of have a lot of stuff in common. If you don't have the derivative, of course, then you have to rely on completely doing optimization types of techniques. So we're going to start with root finding, talk about some of the basics of the kind of iteration schemes we're going to find, what does and does not work, and actually study a little bit of how fast we can expect these algorithms to work. And then towards the end, we're actually going to just do optimization, specifically for functions that maybe we don't know so much about, and then talk about what's actually available out there. Because you could take an entire course alone on optimization, in fact, even convex optimization, which we're not going to do here. So this is a very brief, kind of shallow dive into these questions. If you're really interested in it, I highly recommend taking a course. There's a few of them around, in particular in IEOR, that address these things. Okay, so with that, let's dive in. For this set of lectures, we're going to be returning to a couple functions. We saw this kind of in the motivational lecture. We have this very simple but nonlinear function that's representing how much wealth we've gathered. It's a compounding statement. There are all sorts of different things that could make this more complicated, but this is complicated enough as it is. Again, we have A being the total value after n years. So n is going to be the time variable here, saying it's an integer, or maybe it could be a half year or something like that. That actually works as well. P is payment amount per compounding period. M, number of compounding periods per year. So that's why n has got to be in this kind of full year type of thing. R is the annual interest rate, and n is the number of years to retirement. So we could specify all sorts of different things in here. N is basically going to say, okay, what's the value of this function at some time in the future? If retirement is that future time, that's why we're trying to ask that question. So if we had some of these numbers and we wanted to know how many years to retirement would I have to be to, for instance, be a certain wealth, or maybe I want to add more money, that capital P there, per compounding period, what's the effects of this? So this is all very, very basic questions one might ask if you're deciding that you want to retire and have any kind of wealth left in your name. But this is a complicated function. So oftentimes, we try to find different ways to do this to make it simpler. So say, just for the sake of argument, we wanted to say retire in 20 years. I think all of us in this room are probably not going to retire in 20 years, but you know, it's a goal. So we're going to have P be 18,000 divided by 12. M is going to be equal to 12, and N is going to be equal to 20, just like that. And just to show what this looks like, I wrote up a function. So it's just evaluating this A for us, and I put in a bunch of examples of how to document the function. This is a little bit of a silly thing right now because it's not doing anything particularly fancy, and I have more documentation than I have lines of code. It's not a bad thing. It's probably a little superfluous in this case. But below it here we have, let me blow this up actually a little bit. Below it we have our values that we specified. And I'm again going to have the question of what if I could actually change basically the interest rate. What would how long would it take to get to my goal? So my goal is 10 to the 6th. And we can plot this function. And we see that according to this axis, which is just labeling it in scientific notation, 1 is actually exactly going to be 10 to the 6th, so that's our goal. And then this is the curve as interest rates increase. So this isn't a temporal thing. This is just looking at the interest rates. And it says, well, my interest rate is going to have to be where these two curves intersect. Okay. So that's the problem. It's not trivial, again, to find out where this R is, because in this function, R is kind of buried in here, and there's 2 of them. So algebraically, this is not an easy thing to do. So we could do this computationally. Right? We could just say, I want to get close enough to that and just kind of guess and check. And actually, that is the first thing we're going to try to do, is basically look at a plot, guess where it's at, and then try to adjust our guesses such that we get better and better answers, or closer and closer to that particular piece. OK. So that brings us to fixed point ituration. This is the most basic of ways to do this, and it actually is surprisingly robust. So let's see how we work on it from this perspective. So we decided to do a little bit of math before we started asking our computational question. We got R on the left-hand side of the equation. Okay, so now we basically just divided through by A and then multiplied through by R. Okay? Now, we really haven't done a whole lot for our cause because R is on the left-hand side, but it's also on the right-hand side. So we haven't solved a thing yet. Okay? R has still kind of got that unfortunate exponent on it. So we're going to change the problem a little bit. We're going to say that right-hand side function is going to be g. This function g, it takes in an R. And according to our problem still, we still have R is equal to gr. Okay? And then if I wanted to subtract over g or r on one side or the other, I see exactly why I care about the roots of this particular problem. So we can always return a problem where I'm just trying to find a particular value as a root finding exercise. Okay? So that's going to be the generalization of what we're going to do because we can always do this. So let's actually look again at what this looks like. So same basic thing. Now I just have a function g. That's the slightly modified version of our original thing. This would actually scroll down. So if I run this, you can see the problem looks a little bit different. But by and large, it's still doing the same thing. So that red dashed line now is actually basically r, the function equal to r. So it's just a line with slope 1. It intersects the curve g twice, one at 0 and once at somewhere around 0.08. Okay? So now we have a different problem. We have 2 roots of this function, basically, right? We have one at 0 and we have one at 0.08. The one at 0 is not so useful, so we will throw it away. But we do need to keep in mind that there are now 2 solutions to this problem the way we've done it. Okay? And there actually were multiple solutions before. They were for values of r that were actually negative, which doesn't make sense in our particular case. Okay, so if we plow on through this and we actually just take G and we evaluate it, so I said, well, it looks kind of like the value is near, that intersection point is near 0.08, so 8%. If I plug that in and evaluate my function, G minus R, I get back out this value here. Okay? What I want to get back out is 0. Right? That would give us exactly what we want. So, you know, okay, well, 0.08 was close. It was whatever the result was. It's a little too small. So let's try again. Let's try 0.085. Seems good enough. And sure enough, we actually do get closer to 0. So that seems to be going in the right direction. So maybe we change it a little bit more, maybe change it a little bit less in terms of the amount we're changing it. And we continue to try to get towards what we want. So this is great. This seems to be working. You know, it's converging to 0 with some rate. But, you know, if this is all we're going to talk about, guess and check would take us a lot of time. And we're not using a computer other than to evaluate this function. So there's a lot we can say about these iterations, luckily. One thing we can do is we can just actually code this up. I mean, this is a for loop. You can say, I want to evaluate all the R values and see which one's closest. That's a perfectly legitimate thing to do. So if we actually do that, we can see just for this selection of R's, well, we go 0.08 and up by 0.001 each time. Well, you know, we're getting some values where we want these things to be equal. So note that this isn't G minus R. I don't know why I didn't actually do that, but we're kind of seeing it vary slowly here. And it's, you know, it's getting smaller, it's varying. So we could go through the effort of actually looking at this and coming up with a strategy. But as usual, we like simpler things so we can actually do some analysis. So actually, let's turn to a different problem, something that's a little bit simpler. Our function's x minus e to the negative x, and we're going to just solve for 0. So this would be the same thing as saying, I want to define x such that x is equal to e to the negative x. Okay, so that would be the equivalent problem. But we have our f here, and what we're going to do is we're going to use an iteration for this. So again, if we go to the code here, we're going to be plotting a bunch of stuff today just so we can see things. So here we have x is equal to 0.4. That's our initial guess. All these iteration schemes have to have an initial guess. It is absolutely critical that initial guess is good. Most of these schemes will fall flat in their face if you just pick something, and we will try to go over exactly how you pick things. Sometimes it's just completely problem dependent. Actually, often that's the case, but we'll talk about that in a little bit. Okay, so that's our initial guess, x equals 0.4. I'm going to take 3 steps, so I'm just enumerating the steps. They're going to go 0, 1, and 2. I'm going to print out x, and I'm going to print out the residual, or the error, or whatever you want to say, the difference between what I want to get. And what I'm going to do here is something a little funny. I'm going to take my function e to the negative x, and I'm going to let that determine what x is. Okay? So I'm really saying my function up here, g, x is equal to g of x. So g of x is actually e to the negative x in this case, from how I defined it before. I'm going to say, I'm going to let x in this iteration scheme equal whatever is coming out of g every time. Okay? So I want that to be true. Note that if I did find the right x is never going to change. It's a fixed point. Right? If I put in the x star that's going to solve this equation, then I should get back out x star by definition. Okay? So if x star is wrong, or x is wrong, then hopefully if I plug it into my function and let x equal that, then maybe I can actually get something that's a better guess. That's actually fixed point iteration right there. That's the entire idea. To me, this sounds crazy that this would work. I mean, why would this work? Why should I be able to get a good answer? Well, there are reasons. But you can see here, even taking 3 steps, these are the 2 curves I'm trying to intersect. So the blue one is x, or I guess r in our last example, but this is x equals x. This is e to the negative x. I started with the point marked 1 here. That was my initial guess. The second going through that loop, the second guess was over here. The third guess is over here. And note that I'm actually bouncing around exactly the intersection of these two curves, and that the distance between me and that intersection point, which is what I want to find, is getting smaller. So perfect. If we actually could iterate this to infinity, we maybe can say that I would actually converge exactly to the correct answer. At least that's what this appears to be saying. Okay? Now, of course, we can't go to infinity. We need to put some tolerance on this. We just want to iterate enough that we're close enough that we're fine with that tolerance. So here's just another example where we have natural log of x plus x. Note that this is an equivalent problem. All right, we just took the natural log of both sides of our last equation, and we get this back out. Okay, so analytically, these are the identical questions. Unfortunately, bad things happen for us. So if we go down here, our initial guess was the exact same initial guess. The second guess is further away, and the third guess is even further away. Okay? So something is weird about these functions. We know that they're different functions, but the problems themselves are supposed to be the same. So something's going on here. Something is different between these two things, such that it's not working. Yes?
I thought the initial guess was 0.4.
I mean, I can actually put that in there too. I probably did it because it diverges faster. Or actually, it diverges more quickly. It makes my plot look all funny. So it still diverges. But that is a good idea, though. In fact, actually, we can, if we get a good enough initial guess, this will also converge eventually. Yeah. So initial guesses are important, especially when you're trying to figure out if something's going to work like this. All right, so let's do some analysis, some statements here. First of all, existence. So the existence of a fixed point is something that we kind of hope is there. So is there a solution to the problem? If there's not a solution, we can't really do anything. We shouldn't expect us to have anything. So we're going to say G is continuous on A to B on that range, okay? And then we're going to say the range of the mapping, so basically G is going to take that interval and map it to another interval, and that's going to be at the range of the function. We want y to be, if y is in the range, we want y to also be in the interval A to B. So that's a little bit of a weird statement, all right? If we have x living in A to B, then y, if y is in the range, we also want it to live in A to B. So note that if the function was just multiplying by 1,000, this would not work for various x. All right, we could actually break this really easily. But we can then actually say for all x A to B, then G has a fixed point in A to B. Okay, so whatever this function G is, we can satisfy that condition. Okay. So again, we're actually saying G of x is equal to x. That's the statement that we're trying to solve in this case. So let's test this out a little bit. Okay. So I've drawn the function G. G is in red here. I'm taking a range from 0.4 to 0.8. So that's this box here. And just by looking at where the range is for those 2 points, the range is going to go between 0.4 and just a little bit below 0.7. So in fact, there is a fixed point. We know there's an existence of a fixed point by this theorem. Okay? Now, one thing to keep in mind, I said you could always break this, but you also can often fix it. Right? If it's just a simple scaling, adding, subtracting your function so that it does satisfy this, you can totally do that and then just remember to move it back to whatever the solution is before. So this is just a redefinition of the variables you're in, or you could say, I want to non-dimensionalize this thing and multiply back when I know what the answer is. Okay, so that's a good thing to do in these cases. But this is good. We actually thought this was the case already. So actually, let's look at our second one, which was the log. And in fact, you of course find that with that same range, it doesn't work. Okay, the 0.4 to 0.8 interval that x lives in goes to 0.2 almost to 0.9 almost. Okay, so the range is not contained in the same interval that we chose before. We could, of course, make it smaller. You know, when we were originally doing this fixed point stuff and we were just testing it out, we just picked one value, so we're kind of assuming that we're going to live in some range, or I keep on saying range, some interval that will then give us a range. This is really just saying somehow how far I'm going to be allowed to move if I do this fixed point iteration. Because G, if you remember what fixed point iteration really is doing, it's taking G, plugging in my current guess, and getting back out a new guess. So if that range gets bigger every single time, or it gets further and further away than the original thing I'm looking at, the original window, I might not be actually looking in the right spot. All right, so I can't write on the screen, actually. I have some interval from A to B. X is in here, xk. So that's going to be our kth guess. Starting to use iteration counts here. G is going to take this thing and give me back xk plus 1. So if that ends up being bigger than A to B, that means that I'm going to actually start having to look, or being able to look, further and further afield. On the opposite side of things, if this again is, the range is getting smaller, this is actually, for those of you who have seen this before, this is the contraction theorem. If this mapping is actually going to a smaller interval or the same interval, then I'm actually guaranteed that eventually this is going to converge and give me exactly the fixed point. Okay? So this is the existence of a fixed point. It's going to converge to one of them inside of this thing. There could be multiple. We haven't talked about uniqueness yet. Okay? So that's the basic idea. We want that to happen. Speaking of uniqueness, we can also actually put conditions on G such that we have a unique fixed point, so one fixed point in our interval. Otherwise, we have no idea what we're going to converge to. And in fact, certain cases, you can find yourself bouncing between the two, and we get into trouble that way because we never converge. So now we're going to put a condition on G prime, so the derivative. Again, we're on some interval, and we need a bound on the derivative of G prime. We don't care if it's positive or negative, we just want the magnitude to be strictly less than 1. Okay? And this is just saying there exists one. We actually don't have to prescribe it necessarily, we just have to show it. And if this is true, so basically G is not allowed to vary too fast. Okay? If this is true, then we actually have a unique fixed point in P. All right? So there's all sorts of things that could still be going on here. If G prime is oscillating, but always is oscillating less than 1, we could actually be okay. So that would mean that the actual slope of the original function is varying slowly enough that we're okay. And this again has things to do with how the space is actually contracting. The interval is contracting to something that's nice enough. And we just for all intents and purposes, we could always take the derivatives of things. And we see, in fact, for our e to the x, e to the negative x example, of course, it's got, in the interval we're looking in, it has a small enough slope. So note that if we actually looked in a different interval, we'd be in trouble again. The slope is eventually going to get big enough that we're going to have a problem. All right. So again, got to make sure that we're actually in areas where we can actually do this. Most functions are not going to stay nice enough that this always works. I should mention, if you are actually interested in the exact proofs for these things, just let me know and I'll point you to a real analysis textbook. They usually have a discussion of these things. But this is actually kind of what we really want to get to. We want to understand how this convergence works. Okay? We want it to converge as fast as possible. We also want to show that it does converge. Okay, so we just said that there is a solution and it's unique, but we actually want to know the practical ideas behind how fast is it going to converge and will it converge to one or the other. Okay, how are we actually finding the answer out with our little iteration scheme here? Okay, so now I am going to again add in k's. So k is going to be the kth iteration. The first iteration, if you wanted to count it from 0, would be k equals 0. That would be the initial guess. And then we just run this over and over and over again until we get to some tolerance to what we think is the solution, the difference between x and g of x. Okay? All right, so how does this work? Okay, x star is going to be our fixed point. We're going to say that it exists. If it doesn't exist, we can't do anything. But that means that x star is equal to g of x star. Okay? Once that happens, we are stuck there. Okay? So this is similar to in like dynamical systems or ODEs when you're actually finding fixed points or stability points or whatever you want to call them. This is just this for a mapping. That's all this is. And you can actually use a lot of the same types of ideas from dynamical systems into that. But let's, we really want to know a little bit about how the error or how this residual is going to 0, hopefully. So we're going to do a couple definitions. One is that ek, the little e, k, is going to be the error at the kth step. So the way I'm writing it here is that xk is going to be equal to the true solution plus a little bit of something that gives me the error, or you can flip this around and say xk minus ek is equal to x star. So again, just what is the difference between x star and xk? Okay. Similarly, xk plus 1 is equal to x star plus e to the k plus 1, or ek plus 1. Okay? And just by definition of the fixed point iteration, we have, if we plug in g into g, x star plus ek, we're going to get back out xk plus 1, or x star plus ek plus 1. Okay, so this second relationship here is important for us to keep in mind. All right? So now what we're going to do is we're going to do something that we're going to do a lot in this class, and that's to try to relate ek plus 1 to ek. Because if we can do that, we know what our first error might be. Or we don't necessarily know it. If we did know it, we know what the answer is. But hopefully it's not too big. It's something small. If we can say that ek plus 1 is smaller at some rate with relation to ek, that means it's going to converge at some rate. Okay? If that's not true, then we're in trouble. Okay? So this is going to be the first kind of example of how we're going to use this. And we're going to make some definitions that will actually apply throughout the class. But this is kind of the first step in this. Okay. So how do we do this? Well, let's write down a few things because I'm going to go to the next piece of this. This clean worker works. We're going to say xk, kind of dying. All right. Okay, so that's just rewriting what we have there. All right. So if you have the notes open, or you can guess and act like you really knew the answer. That doesn't matter. What can we do? We want to relate ek plus 1 and ek. There's a generic function g there. That's no good. We have no idea how to get ek out of there. So what can we do? Assuming g is nice enough. Seen them before. The name of them begins with a capital T. Taylor series. We're going to use Taylor series a lot in this class. So if I ever ask a question like, what should we do next? Taylor series is a pretty good answer, almost always. Especially in this case where if we have generic functions we're dealing with, the only way to get stuff out of those arguments is using a Taylor series. So we're going to center this Taylor series about x star. Okay? And ek is going to be one of the values coming out of this. Okay, so let's do this. So we have g of x. So this is the generic Taylor series expansion about x star. Okay, so we have g of x star. We're just evaluating at the thing we want, plus subsequent derivatives of g. All right. So Okay, well, this isn't so bad. X minus X star, if I was actually going to evaluate the series at another point, say xk, I would get back out something else. But what we really want to do is we still need to get into what this thing is. So I'm going to take my expansion up there on the top, and I'm going to plug in this business. Okay? So now I'm going to get gx star plus ek. And then everywhere we see an x, I want to replace with again, x star plus ek. So that's where this line comes from. Okay, so I get g prime evaluated at the fixed point times ek, and I just get ek. So note now we've actually extracted ek from the argument in g. G is also actually now evaluated at x star, which we know what that is, because it's a fixed point. All right? And then we start seeing higher and higher order terms. Okay? So ek to the cubic power out here, this is asymptotically what the rest of this stuff looks like. And ideally, hopefully, what's going to happen is ek is going to go to 0, which means that anything multiplied up here by ek is going to get smaller and smaller, faster and faster because of that power on that right-hand side. Okay? So now we're going to plug some things in. We, for instance, know that by definition, gx star plus ek is x star plus ek plus 1. All right, exactly what we wanted that thing. So the left-hand side turns into this. We no longer have a g. We do know gx star is equal to x star. Note that we have those two things on either side of the equation, and they cancel each other out by definition. So we get ek plus 1 is equal to g prime x star ek. We don't know what the x star evaluated at g prime is. We've never put any conditions on that. So that's going to stick with us. And then we have higher order terms, g double prime, and so on and so forth. So rewriting this, throwing away higher order terms, we're left with this. And we can bound this. In fact, the important piece of this here right now is that g prime, x star, is going to be, if this is actually less than 1, this is exactly the thing we found for one of our conditions for uniqueness, that we have this relationship here. This actually should be probably a less than sign. So it's the absolute value of ek plus 1 is less than or equal to capital K times ek. So if k is less than 1, that means this thing is shrinking. So higher and higher orders of k, each subsequent term in the sequence is going to get smaller and smaller. That's why we want k to be strictly less than 1, and we can bound the error. Now, if k is really, really close to 1, it may take a very long time for it to converge. That's a sad state of affairs, but as long as it is strictly less than 1, we're fine. It eventually will converge as long as we wait long enough. Now, there's another part of this here. If we had a power, right now this is a linear relationship. Right? ek plus 1 is equal to some slope ek. If there's a power here, then every single time we'd actually come up with a new ek plus 1, that means it's going to actually converge even faster. So this constant out in front of this, we generally actually we're not too concerned about it. It can be bad for us, but we're not so concerned because what we really want to do is see powers on this. So right now this has just got a power of 1. But you could imagine we might be in a better situation sometimes. So for the rest of the class, like the rest of the semester, we're going to be using these types of claims. And actually, we saw an example of this in the error lectures on Tuesday. We're going to have an error relationship, ek plus 1 and ek. There's a capital C here now. I'm going to throw out a k. C is strictly less than 1, and there's some power n. If n is equal to 1, which is the case we just found, we say that this particular algorithm is going to be linearly convergent. Right? It's a linear decrease in the error as we keep on iterating. If n is equal to 2, clever us, we're going to say it's quadratically convergent or second order convergent. Okay? And then you can say cubically convergent. You can keep on going with this. Usually what I'll probably start using is, although these are also fine terms, I'll say first order convergence is linear convergence. Second order is quadratic. Third order would be cubic. It's just an easier thing to say. So when we're talking about orders of convergence, this is what we're talking about. What is that value of n? And there's a lot of times that's going to be the focus on how do we get that value, and we want that to be as big as possible, and what are the costs of getting that big value there. Okay. Similarly, if c is greater than 1, we say this scheme is divergent. It's not going to converge. It's not useful. Shouldn't say it's not useful. Sometimes divergent things are useful. They're just very delicate to deal with. But generally in this class, we're not interested in divergent things. It's just not very helpful for us. Okay? So these are going to be definitions we're going to see time and time again throughout class. And this is how we're going to actually describe most of the algorithms and methods that we're going to run into. Okay, so just to kind of look at some of these things in light of these, we can actually just calculate some of this stuff out. So with x star approximately equal to 0.56, we can calculate the derivative of this thing, and we find out that it's approximately the same thing. Okay, we're about where the exponential function just gives you back out the exact same answer, which is what we'd expect. That was the thing we were looking for in the first place. Natural log. So if we take the natural log, take its derivative, and look at what the value is near this x star, which we think solves the problem, we see that the derivative is, in fact, actually quite large, or larger than we need it to be. So this is not going to converge. We'd have to come up with a different way to solve this problem. So again, these are actually equivalent questions. We're just looking at them mathematically slightly different in an inverted way, and it turns out that's not a good thing to do in this particular case. And unfortunately, we really can't actually do this in general. So we could also do it with this thing. So we can take derivatives of this. That's maybe annoying, but it's definitely doable. But there's other ways to do this, and this is just another example for you if you would like to do this as well. So we're using SymPy here. In SymPy, you have to define the variables that you want to use as symbols. So I'm defining R, P, M, A, and N as symbols up there, and then I just stick them into variables. So this is really saying I can now use this thing to represent the function or the variable R. Okay? So you just have to tell it this to begin with. And then I'm going to define G is equal to my function. So this is just literally just G. And I can tell G.diff is going to take the derivative of that thing with respect to R. And I'm done. Going to do everything for me. And I can evaluate these things like this. So here's another nice command to keep in mind. That's the substitute command. So if I just wanted to evaluate this G at these values, it's going to give me back those values. There's also this thing called lambdify. So this actually turns it into a function you can evaluate, just like it was any other Python function. So that's exactly what we're doing. We're plugging in some values into G prime, and then actually this is telling me that this is going to be a function of R. It gives me back as F, because that's not using the F we had before, but it works. So if I evaluate this thing, this is the actual G prime. So I did the derivative for me. It turned it into a function, and now I'm evaluating it. And you can see that we actually probably are going to be in trouble if we're not very careful about how we do fixed point iterations. And in fact, I was very careful in my guesses from before, because if you're not, fixed point iteration does not work on this function. So be careful. It's really what it comes down to. All right. Is there any questions about that so far? All right. Okay, so we've seen fixed point iteration. Most of the stuff, actually, even though fixed point iteration seems pretty tricky to get to work, or at least there's a lot of stuff going on, it is actually the basis of a lot of what we're going to do. We're just going to be a little bit more clever or add a little bit more knowledge to these iterations. Okay. So again, we're going to go back to this general idea that we have the roots satisfy something. So we still have G of X star is equal to X star. X star is always going to be our fixed point. But we really want to do, say, root finding, find me the zeros of the function such that X star is going to be the values of those roots. Okay? So just basically the same definition we saw before. All right. There are many, many different ways to do this. I'm going to show you 3, and then make some comments on what actually is used in practice, which are some combination, actually, of these 3 usually. But there's all sorts of different ways to do this, especially when you get into higher dimensions. If you have to find those types of things, it's very problem-dependent what you should do. But most of the ideas are actually fairly simple and are represented well by these classical methods. Okay. So let's dive right in. Okay, so bracketing. So bracketing, it's just a definition. A bracket in itself is an interval that's defined, and we're going to say a bracket is only a bracket if it contains exactly one zero, and then when we get to optimization, one minima and maxima. And, well, one minima or one maxima. So basically, we're close enough that we don't have a bunch of stuff inside of a bracket. Doesn't mean A and B couldn't be like gigantic, right? If I took a parabola, as long as A and B are outside of the one place I'm trying to minimize that thing, then it could be the entire real line for all I care. All right, so it doesn't necessarily mean that's small, but we just want exactly one thing in it because we're going to make lots of decisions based on there only being one thing of interest in this interval. In the case of a bracket in terms of a zero or a root, we can actually know whether or not it is a root if the sign of f of a is not equal to the sign of f of b. All right, so that just means that I have a function. It's going to have to cross the x-axis at least once, in fact, only once. And if that is true, the sign has to flip on the ends of my interval. All right, so for instance, if I had the function look like this, okay, this is the x-axis in this case. Just use that red marker. That red marker is really good. Okay, so valid brackets would be, for instance, this one. Right? It contains only one root, and the sign on the function flips. All right? Another one would be here. It would be a different root, so that would be fine. But note that I can't do one that actually encompasses both. All right, if I picked one that was here and here, the sign does not flip because there's not a unique root. All right? So an actually very seemingly simple type of check actually completely makes my job a lot easier. I can always just check this. I always know that a bracket's valid and that there is a single root inside of there if that's true. Okay? In fact, this thing can wiggle up and down. It can be as many roots as you want inside of that thing. I can still use this to make sure that whatever bracket I picked is going to only have one thing in it. Similarly, if I have a single minima or a single maxima, then I want the sign on the derivative to be not equal to each other. And this is, of course, you just take the derivative. Then now you're finding roots again. All right? Now, that doesn't necessarily mean you actually do have a minimum or maxima, right? This could actually be a saddle point or something more complicated. But we're still going to say a bracket has to have this property in order for this to work. And again, we'll investigate how that works when we come to optimization. All right. So we're going to let our function f of x that we're trying to find the roots for, in this case, we say it's continuous on a to b. Has to be nice enough. It's jumping all over the place. Weirder things can happen. We're going to say the sign is not equal to itself. So we have a root in our interval or our bracket at this point. And then we're going to say, of course, there exists a c such that f of c is equal to 0. Okay? So this is really just saying exactly what I just said. There is only one 0 inside of that bracket. We can basically see why that is. But we also can use kind of advanced calculus. It uses the intermediate value theorem to make sure that indeed there is a c. So that continuity is actually important. Otherwise, the intermediate value theorem actually kind of falls on its face. Not always, but it's much harder to use. Okay. All right. So here's just an example. This is actually based on what we were just looking at. Again, we have a bracket picked by having this endpoint A and the other endpoint B. There's something in the middle of it, just exactly how we thought it would be. I'm using this interest rate problem for this. Okay. So we know things, we've defined things, and we know that exists a solution if we have a bracket. So algorithms and methods that we're going to consider are basically going to be just picking brackets, trying to figure out valid brackets, and then shrinking those brackets until that bracket shrinks to the point where you say, well, the difference between A and B is small, you divide it by 2, or whatever you want to do, just pick A and B, and that's my solution. All right, so if I can always pick new candidate brackets that are always getting smaller in size, the actual size of the interval is always getting smaller, I know that I'm going to converge eventually. Okay. All right, so how do we do this? There's lots of different ways. One way, given a bracket, so that's my initial guess, and a function f of x. What we're going to do is we're going to say, I'm going to cut my bracket in half, because why not? You know, half seems good. And then I'm going to take that bracket, check the two new brackets, which one is actually a bracket still, right? Only one can be a bracket, because I only have one fixed point. Unless I was super, super lucky, and exactly halfway in that middle, I exactly get the solution, which you should check for. You know, that's obviously something to do. One or the other is going to be the next bracket. I've halved it, so it's getting smaller by a half. They're always shrinking. I always guarantee that. And as long as I can, of course, pick which one's a bracket by checking the sign on the endpoints, I'm done. This is bisection. Okay? So what does this look like? It's going to be our first coding exercise. So there's a bunch of things to define here. I provided a bunch of stuff to plot, so we're going to see how this actually works. There's some algorithm parameters you should think about. I've also said, well, I've initialized the bracket here. And there's some loop stuff here. So we need to initialize the loop based on this code up here. So initialize the bracket. Any variables that are going to be updated inside of here, they have to start somewhere. And then there's some sort of checking of the tolerance. So once the interval size, or the bracket size, gets below a certain point, then we want to stop, because we're satisfied. It's never going to, you know, in a finite number of iterations, we can never guarantee we're actually going to get the true solution. So we do have to stop at some point. I've done a little bit of stuff here, like I'm saying there's a maximum number of steps, because if I don't converge after, say, 1,000 steps, we want to fail. Okay? Maybe it's just converging too slowly, or we just have to be more careful. And then inside of here, we're going to have to check and actually come up with our new bracket. So I'm going to give you a few minutes to think that over, try to code it up, look in the notes for the actual solution. Just think about this a little bit, and then I'm going to code this up and walk you through some of the logic, and we'll kind of see how this is going in terms of our convergence orders. All right, so I'll give you a few minutes for that. Work with people around you if you'd like. See what you can do. Okay. Hopefully you've had at least a little bit of a chance to think about this. But let's implement all of the missing pieces here. Just in terms of a style, I generally, when I have parameters that are constants, this is somewhat generic to programming practice, but we capitalize those variables just to let people know. You can do whatever you want. I just happen to do this here. So in this case, I'm going to say 10 to the negative fourth is the tolerance. So that's the size of the interval or the bracket when we're going to stop. We're saying we're close enough. And we'll just make a big max steps. So there's a bunch of variables. And again, there's all sorts of different ways to do this. You don't have to use what I did. I did use f underscore c or f underscore a, f underscore b, just to store function values. You could have just evaluated the function. The function isn't that expensive, but you could imagine that the function would take an hour to evaluate. This might go slowly. So that's why you may want to store the output from functions. And that's what we're going to do here. So delta x is going to just be the size of my interval. Okay? So we're going to keep track of that. We need to check it anyways, so we might as well compute it. This is based on already that I've already picked my interval, my bracket, which is up here. And I've checked to make sure that there is, in fact, a 0 inside of that. C is going to be the new midpoint. Okay, so A and B and then C right in the middle, which means that I can actually calculate this all sorts of ways, but one way I can do it is to say the original size of the interval from B to A, or A to B, is delta x. So if I divide that by 2, that's the new size of the new intervals. And A plus delta x over 2 is going to be the middle value in that new bracket, or that new interval. These are going to be simply just be the evaluations of the function. Okay? So we're going to use these variables inside the loop when we just need to have the first time round have them initialized. That's what this is saying. In fact, we're going to actually plot exactly where C and f of c is. And that's what these two things are doing. So now we have to actually write the loop logic. First of all, what we want to do is check to see if we actually have either decreased enough of the bracket and we're actually below the tolerance. So that's one thing we want to do. We also could do things like say, all right, well, f of c is exactly equal to c. We may want to check for that. The way to do this both is to actually check the value of f of c. Okay, and then that's actually saying basically like we've succeeded. F of c should be equal to 0, and that tolerance is going to tell us that that's the case. We could also check to make sure that the interval is below that tolerance. This is a very similar type of question, because if f of c is close enough to the tolerance, or close to 0, enough for this tolerance to check to be true, that also means that my interval also has to be small enough that that's true, because f of c is right in the middle of it. Okay? If this is true, we want to stop, and I'm going to break out of the loop. Okay? I've completed everything I want to do. There's a lot of different ways, again, to do that. All right, so that's just checking to see if I've succeeded, but we have to actually do something inside this loop. So what I'm going to do is I'm going to check the sign of f of a, and if it's not equal to the sign of f of c, then I know my new bracket is going to be a to c, right? And I also know that because of that condition, that is truly a bracket, and that's the one we're going to choose. Okay? So then what I'm going to do is I'm going to say set b now equal to c, because that's going to be my new bracket definition, and I'm going to replace f of b with f of c. Okay? So note that I'm actually not ever going to be evaluating the function more than once at a particular point by doing this. If that's not true, that means the other bracket has to be the right one, unless we're close enough to the thing which we just checked for, close enough to the 0. So if that's not true, then we do the opposite. We say a is equal to c, and then we replace f of a with f of c. Okay? So that's choosing our new bracket, one or the other. Then we just reset some of this stuff. So we could actually set delta x to be just half of what delta x was before, but you can also just compute it using b minus a. It's a little safer. The new c is going to be, again, the same thing as we had outside the loop. And then this is the only time we actually evaluate the function f again. So with this, if I haven't screwed up, yes, so it converges. So the way the logic is happening here, it's going to continue to do these loops until I break out of it. So until this is actually true, it's going to do it unless it gets up to max steps. If it gets up to max steps, this loop is going to terminate because it's the natural thing for it to do, and which is why I'm checking steps is equal to max steps. That means that I haven't terminated the loop, which means I failed. This is one way to do the logic for failure. And this is an important thing. If you get out of an iterative loop and you may have actually used all your iterations and you didn't check to see if you succeeded or not, you will get points off. That is not a good thing to do. You always want to know whether you've succeeded or not, because otherwise you'd have no idea. Okay? In this case, we're going to say if steps are equal to max, then we're going to assume that we failed. If not, we'll say we were successful, and we'll print out exactly what the values are, and then also how many steps it took us to get there. So I just ran this. So you can see the x star, this fixed point, is 0.89, 856,024. Well, you get the point. The value that we came to for f of x star, again, we want this to be equal to 0 if we succeeded. It's 10 to the negative fifth. And it took 30 steps to get there. Okay? And this is just a demonstration of what's going on. You can see 2. The first iteration is actually going to be the A and B brackets that I've actually provided, which are these dots. It gets kind of jumbled in there, so we can actually come up here. We only do 4 maximum steps, just for illustration. You can see we've reached the maximum number of steps because we didn't take 30. But you can kind of see the numbers a little bit better here. Again, the first iteration is going to be the first one here, which is why it's not being labeled. 2 is going to be the first guess. 3, 4, 5, you can see that we're actually converging in each time we have the interval to that root. Okay? So something that actually didn't seem to work for fixed point iteration does work in this root finding business. Okay? And doing it fairly quickly. So I want you to, let's actually go this 1,000. Keep the number of steps in mind, though. All right, we took 30 steps. The real actual difficulty here is evaluating that function f. That is going to be, however complicated f might be, that's basically going to be our assumption. So that's always the most expensive thing. So taking 30 steps means we have 32-ish different function evaluations that we had to do in this case. We could also actually increase this tolerance. So we can go up to 10 to the negative 8th. And of course, it takes a few more steps to get down. Okay? So not twice as many, which was good, and not that many to get there. So you can play with that too. But keep 30 in mind, as we'll do 10 to the negative 4th before time. All right, so that's bisection. Okay, so now let's talk about convergence of bisection. Again, we generally want the type of expression we have here. The absolute value ek plus 1 is equal to or less than is usually the statement we'll use. And we need to know what that capital C is. If C is less than 1, we're good. And it also has to be greater than 0, of course, because if it's negative, we're going in the wrong direction in that case too. But n could actually be any value greater than 0. It could be fractional, like a half. It would be square root. We will see those occasionally, and those are always sad times. But for this case, we're going to consider that this is the type of thing. We want to know what make sure that capital C is strictly less than 1, and we want to know what n is for this particular algorithm. In this case, we actually are going to use some arguments that seem simplistic, but give us a nice answer, and that is that ek, so that error, the difference between my root and the true solution, is going to be on the order of delta xk. Delta x being how we defined it is the size of our bracket. Okay? Now, that's actually an upper bound, right? In general, unless we're super unlucky, well, even if we aren't super unlucky, this really should be a half. Right? We're always going to be at least somewhat close to the true root because of the fact we know our bracket contains it, which means if I'm at A or B, I'm going to be somewhat close to that, that thing. I just have to pick which one I'm closer to. Okay? So this is an upper bound, but it still works. EK plus 1, it's going to be half of delta xk by definition. Which now, because I'm saying that EK is going to be bounded by delta xk, EK plus 1 is going to be approximately 1/2 delta xk. I can now relate EK plus 1 and EK to get EK plus 1 is equal to 1/2 EK. Okay? This isn't using very much at all, right? We've basically just used the algorithm description of the bracket, having a bracket that has a point in it, and I get out that this is a linearly convergent iteration. Okay? So it's linear. It's not so fast, but this isn't using anything about whether or not the function is nice, other than the fact that we have to have the existence of that stuff. It's just saying that if I have a bracket and I do this iteration, it's going to converge linearly, which means that bisection is a very, very robust algorithm to do this. Okay? Which is why we like it. All right. Newton's method. So Newton's method you've all heard of, I'm sure. It is a root finding exercise, right? And we use more information. So that's its advantage over bisection. We know that given a bracket, bisection is guaranteed to converge linearly to a root, okay? But if we can use more information like we do in Newton's method, it can actually show that it's going to converge faster than bisection, but we give up the fact, two things. We have to compute a derivative, or find some approximation to a derivative. Also, we know that Newton's method can be slightly cranky. We have to give a really good initial guess, and there's some situations where we won't get a solution at all. We won't converge to anything. Okay? So let's actually go through this a little bit in our time remaining. The basic idea and derivation. One way to look at this, and actually, I don't know if I like this better than the other way, but what we're going to do is we're going to say we have a function. Okay? It can be some crazy function, and I'm at a particular point. So in this case, the bracket is really just saying maybe I'm at one edge of the bracket, and then I know I don't want to go outside of the other side of the bracket. So the bracket's still living in here. It's just a little bit more abstracted. But anyway, I'm going to have some derivative information about my function, and instead of dealing with the function, which I don't know what it's doing in general, I'm going to say, you know what, function, I want to approximate you with a line, because I know how to find the zero of a line. So this is you could think of this as an interpolation scheme. Basically, we're modeling the function with an approximation and using the approximation to find the answer, and hopefully it's good enough. Okay? This is actually the basis of a lot of different numerical methods. Model something or change something into something you know what to do with, and hope that that's good enough or approximates the original, more complicated thing better, or well enough that you can get a good answer out. Okay. So that's the first way to derive Newton's method. So here we go. We want to find the function, or this approximation to the function. We're going to call it y. Y is equal to f prime xk times x plus b. So we do need to have that y-intercept piece to this. Well, okay, so I know what f of xk is. Right? I can just evaluate it. So those are my two pieces of information. I have f evaluated at xk and f prime evaluated at xk. I plug in xk, I solve for b. Okay? I have enough information here to write down then the approximation at this point xk, and this is what I get at the end there. Okay? So the slope times x minus xk plus the y-intercept piece. Okay? So, all right. Now, we have our line. So y is equal to some function of x. We find the 0 of this thing. We know how to do this because it's a line. We plug in y is equal to 0 and solve for x. Okay? And we get out Newton iterations. So that's all there is to it using this type of idea. So xk plus 1 is equal to xk minus f of xk over f prime xk. Now at this point, you see one of the problems. If the derivative of f ever vanishes, we are in trouble. That's going to blow up, unless f is doing something nice for us as well. And of course, that's going to be the major downfall of Newton's method. We need to be very careful about what f prime is doing. It could actually lead us into problems. But this is a perfectly good algorithm if you have all this information. Note that this is there's a little bit of a difference here. If you're actually, this is just for the scalar case. For the like a system of equations, you actually have to solve a linear system of equations to get this back out. You have to invert the Jacobian, and it becomes much more expensive. We will eventually actually kind of delve into that a little bit later in the class, but keep that in the back of your mind. This is only simple because it's a scalar case. All right, so what's the alternative? Taylor series. So, okay, so apparently this is that was the only time the answer wasn't Taylor series immediately, but of course we can use Taylor series. We're going to approximate the function as it's Taylor series centered at xk, because we know xk. Okay? So if we do this, we get out all these terms, f of xk, f prime xk, x minus xk. So, and we're going to cut the series off here. Not so surprising. We're going to also define something a little bit differently here. We're going to say xk plus 1 is equal to xk plus delta xk. So that's just going to be the change in the value of our new guess. So we can actually look at delta xk to see how we're converging, for instance, because that's actually giving us our step. And there's actually all sorts of different ways you can modify Newton's method by actually specifically controlling how big this can be. Maybe you computed what delta xk is going to be, and that's actually kind of the way it's often thought about. But if you said, I wanted it to be 2, or it should have been 2, and I don't want to, I want to be more conservative, so instead I'm going to multiply it by 0.5 and only take a step 1. So that's a modified version of Newton's method. We're not going to talk about that too much. Just know that that is a thing. Okay, so we have the difference. We have the function approximation using Taylor series. We're going to plug in xk plus 1, which we know is equal to this thing. So we get out the delta xk's. Okay, so we have xk plus 1 is equal to f of xk plus the derivative times delta xk. Note that we don't know what this is. If we did, we'd already know what xk plus 1 is. So that's not great yet. But that's OK, because we can get rid of it eventually. So this is the thing that gets a little tricky. We're actually going to assume a fixed point iteration type of scheme at this stage. So we're going to say xk plus 1 is equal to x star. So we were really good, and we guessed exactly what we needed. You know, maybe that's not so great. Basically, this is going to actually have some of the caveats from fixed point iteration again. But if we do that, then we know that f of x star is going to be 0. So that was f of xk plus 1. This doesn't change on the right-hand side, but it does allow us to start to actually solve for delta xk. In fact, delta xk, if I truncate the series here, I forget all the rest of these terms, is exactly this, and then you can just write that down Newton's method in that case. Now, the one advantage to this stuff is that, or this particular type of analysis, is that we actually see what the error we're making in the approximation. So the second derivative with respect to f is going to control how well we're going to do from time to time. Okay? So I'm going to stop there, so we're running out of time. Next Tuesday, we're going to come back to this and start to go through the analysis, why Newton's method is great and why it's horrible. So have a good weekend. I'll see you later.